Hey guys, so in today's video we're going to be talking about the series and parallel circuit basics. We're going to go through a few examples. We're going to talk about the difference between series and parallel circuits and how to solve some of these questions. Okay, let's get this started. So first things first, what is a series versus what is a parallel circuit? Well, as you can see here on the left side, we have a series circuit. Um, Something you could tell straight away is the current does not split. It's the same throughout this whole circuit. That is complete opposite to what parallel is, as you can see on the right side. There's current going through here, 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 and here, and coming all the way back down to there through the battery source. So that's the key difference. You see that the current splits in a parallel circuit rather than being the same throughout the circuit like a series. And in a series circuit, the voltage is not the same across each resistor. As to a parallel circuit, the voltage is the same. That's because, as you can see, this voltage source right here, this whole upper part right there, that all is one node. So you could say that it has the same the voltage drop across all these resistors are the same. Um, and those basically are the key differences in distinguishing what's parallel versus what's series. Now that you know that, let's move on. So how did I know the direction of the current? So as you can see here, I just assumed the polarity of the current, like the direction of the current right here and right here at the very start of the video. How did I know that? Well, you could see I have a little drawing that looks something like that. And what is these two lines right here? Well, that's just a battery. It's the battery is the bigger side is the positive and the smaller side is the negative. So now that I know that, well, how do I know the current's flowing out the bigger side? Well, current flows from higher potential to lower potential always. That's just a rule you have to remember. Um, how I think of it is kind of like I kind of compare it to gravity, like gravity potential energy. And gravity flows from high to low. I kind of think of it like a cliff. That's just an easy way for me to remember it. But yeah, that's just something you have to know. So you always, current always flows from higher potential, the positive side, to lower potential to next. So the current would be flowing like that way. So that's just something to mention. Oh, okay. Um, you could think of a resistor like a light bulb, kind of. Like light bulbs in parallel will always be brighter than light bulbs in series. Let me tell you why. So if you have something in series, uh, the more resistors you add, for example, I have something that looks like this. The more resistors I add, right, the higher the effective resistance is going to be. Okay? And if the effective resistance is higher, that means the current is going to be lower. This is simply because Ohm's law. You have V equals IR. This being the voltage, this being the resistance, and this being the current. So you have V equals IR in that relationship. So the higher that your resistance is going to be, the lower your current is going to be for series. And since the current's going to be lower, the more light bulbs or the more resistors you add, you could think about that interchangeably. Uh, the the dimmer your lights are going to be in series. But if you have something in parallel, okay, you have something in parallel, like something like this, okay, and these could be thought of as light bulbs. Like it's the same thing as drawing them like that, like a two light bulbs in parallel. So if you have two in parallel, the opposite thing's gonna happen. It's actually gonna be brighter compared to if you have like two in series, for example. It's gonna be brighter. So if you add up if the resistance in parallel, the resistance is gonna go down, and the current effectively is gonna go up, as you can see from Ohm's law relationship right there. So that's really important in real life applications. You're not gonna, if for example, you want a brighter light, you're not gonna want to add a bunch of lights in series. Okay, uh, so how do we calculate uh, this R effective? Okay, so what R effective is essentially if you have a bunch of resistances, in a circuit, like you could say like that, for example, right? And then let's just say you have a battery right there. R effective is just the one resistance that is representing all of these resistances combined in one circuit. So R effective will look, the circuit can be represented like this through the R effective. Now, how do we calculate R effective? Well, it's different if you have a series combination or a parallel combination. Whenever you have a series combination, the R effective is going to be R effective equals R1 plus R2 plus R3 dot 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 dot. So like whenever you have something in series, you just simply add them like you would anything. So let's say I have this right here, A and B. So the R effective, RAB, in this case would be R1 plus R2 plus R3. Now, if I have something in parallel, it's going to be a little different. Your R effective is going to be equal to 1 over R1 plus 1 over R3, whoops, 1 over R2 plus 1 over R3, dot, 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 and you keep going on, and you raise all of that to the power -1. So, if I have a simple circuit like this, a parallel combination like that, R1 and R2, the R effective here would equal to 1 over R1 plus 1 over R2, all raised to the -1. Let's move into some examples um, so we could solidify what we just talked about. So as you can see here, there's 3 resistors, and you could look at it. The current would be coming through here because it's going through from positive to negative, and it's all traveling in the same path. There's no current split, just like all the way up here you saw that the current was splitting. It's just current going through one path. You can kind of imagine it like one electron moving through the wire, going through one path. It doesn't have to pick and choose, should I go left or should I go straight? It just has one path. Some people might get confused about this resistor right here. Oh, why isn't this resistor, drawn somewhere there or something like that? Well, that effectively doesn't make any difference at all. I could have drew the circuit in the exact same way, like this, and it doesn't matter because they're still all in the same path. So it really doesn't matter how you draw the circuit as long as they're in the same path. So now that we could agree on this looks like a series circuit, how are we gonna solve this circuit, So we could find the R effective, and we know from the previous formula I showed you guys up there that the R effective is simply just all of the resistors added up simply. That's it. So 3.33 plus 3.33 plus 3.33. That's going to be your R effective. So R effective equals approximately 10 ohms. Okay, now that we found R effective, what does that mean? Like what can we do to the circuit now? Well, we can redraw the circuit as one resistance with a voltage source. So you got your 10 volts up there, and we could redraw 10 ohms. We could redraw those. We could go from what we had up here all the way to this. So what can we do with this now? Well, the whole point of finding these R effectives is essentially to solve for something else, whether it's like you're trying to make it your life easier finding voltage or current or whatever you're trying to find. In this case, we have voltage. Voltage is given to us, and we know that V equals I R. So we have voltage. Voltage is here, let me write this down here. Voltage equals 10 volts, and we have resistance. R equals 10 ohms. So we have these two, and we could just simply rearrange Ohm's law and solve for current. So we could say I equals V over R, which is going to equal 10 volts over 10 ohms, which is equal to 1 amp. So we found this current going through the circuit. The current is 1 amp. Okay, let's move on to a parallel example, and then we'll move on to a slightly more complicated example after this. So we could see that right here there's a current split, and it comes back right here. So we know that these two 5 and 10 ohm resistors are in parallel. So we know that our equation for R effective is 1 over R1 plus 1 over R2 to the power of negative 1. Now, if you get a calculator and solve, you will get your R effective as 3.33 ohms. Now that we have that, we could redraw the circuit. Whenever you find your R effective, it's a good idea to redraw your circuit. 3.33 ohms. And this is how our circuit looks like. So what can we do with this information? Well, we can find the current, just like we did last time. So we have V equals I R. I equals V over R. And you just sub in your values, and you're gonna get approximately 3. Okay, so the current in this circuit is 3 amps. Now let me ask you something. What current is 3 amps? Because you could look at the circuit and you could be like, well, there's current going through here, and coming through here, and coming through here, and coming right back here. So which one is it? Well, you solved the current based off of this circuit right here. So the current you solve for is this. That's the current you solved for. Whoops. That's the current you solved for. So what current is this corresponding to the circuit we have above here. That is this current right here. So we know that this current, is equal to 3 amps. Now what if I ask you, I want to solve for the current going through the 5 ohm resistor and the current going through the 10 ohm resistor. Okay, well there's something we can note. We can note that the current going through these two resistors added up is going to be equal to 3. You could also go about this problem a different route. In my opinion, this is the easier way. And we're going to use something called the current divider. So current divider has a formula. The formula is I, whichever I you want. So let's say we want to find I1. I1 equals I total, the total current, so the 3, times R2. Now, which one is R2? R2 would be your 10 ohm, and R1 is going to be our 5 ohm. So it depends on the resistance in the opposite branch. Keep that in mind. That's where a lot of students make mistakes. And then you're going to do R1 plus R2. So this equation right here, that is called your current divider. Okay, so now that we have this equation, we can solve for the current going through the 5 ohm resistor. So let me ask you something before we solve. Looking at the circuit, which current do you think is going to be higher, I1 or I2? I'll give you a second to think about that. Well, now that you guys have your answers in your head, I'm going to explain to you which one it's going to be. So there's more resistance in the 10 ohm path than the 5 ohm path. And if you think about it, the more resistance something has, the harder it is for current to travel through it. So the current is going to be higher wherever the least path of resistance is. So the current is going to be higher for uh, the 5 ohm current path. You could also look at this equation, the current divider equation, and you could tell, well, since it's going to be multiplying by 10 up here instead of 5, you could say that just by looking at those numbers, you know that the 5 ohm path is going to be higher current. So let's solve for I1. So you're going to have 30 over 15, which is equal to 2 amps. So your I1 is equal to 2 amps. Now, going back to what I said before, this I total is 3. And your I1 and your I2 has to be equal to 3. So you could say that I total, which is 3, we know that, equals to I1 plus I2. And you could simply solve for I2, now that we know I1, and say 3 equals 2 plus I2, then rearrange I2 equals 1 amp. And you will also get the same answer if you simply just plug it into the current divider, which is usually what I prefer to do because it avoids any silly mistakes. So let's double check the current divider. So this time we want to find I2. So I2 equals to I total times R1 this time. So every single time you'd write down this formula, the only thing that changes is what you're finding and then the resistance at the top. So the resistance at the top is, this time we're going to be talking about R1. So as we mentioned before, the current traveling through a path depends on the resistance on the opposite path. So keep that in mind. That's also something students mess up on a lot. So we talk about the opposite resistor when we're trying to find a specific current. And then it's also just going to be R1 plus R2. So you're going to have um, 3 times 5 all over 5 plus 10, which is 15 over 15, which equals to 1 amp. And that is the same answer we got over here when we just looked at the circuit and tried to solve it by looking at it. Now, let's move to a little bit more complex problem here. Now, in this circuit, you see that there's nothing really obvious like shouting, oh, I'm series or I'm parallel. But remember the basics. Go back to what we talked about before. There's current splitting over here and over here. So couldn't I say that the 3K resistor is in parallel with the 6K resistor? It's the same thing as drawing it like like this. 3K and 6K. This question just drew it a little weird to try to throw people off, but at the end of the day, those are still in parallel. And in this circuit, we have series and parallel connections. Last two examples was only one or the other. So yes, we can solve for the R effective, but we just have to break it down into smaller steps. Okay, so what I like to do for these types of problems is I like to solve for one chunk and redraw the circuit, then solve for the next part and redraw it, and the next part. And a lot of people would disagree, but I think that's the best way to do it, just because most of the time you're going to be asked to solve for a specific current and stuff. And if you have all the circuits redrawn, it's easy to backtrack and solve for that current rather than have only two circuits drawn and have to redraw something else. So let's start this problem. So first things first, we noted that the 3 and the 6 are in parallel. So how do we add those? So R effective equals, remember, 1 over 6 plus 1 over 3 all raised to the negative 1, which is going to equal 2. 2k ohms. Okay, now we could redraw the circuit. Oh, let me just put there. We could redraw this circuit. 10 volts, 1k. And there's going to be another 2k here, which is what we just solved for. Now we have something like this. So what can we do next? Well, now we see that this little chunk right here is in series. So we can add those in series and redraw the circuit. Again, 10 volts. And we have the 1k here, 4k. And again, how do we add something in series? Well, you simply just add it. It's R1 plus R2. So this is going to be 2 plus 2. So we're going to have 4 here. Okay, well now that we have this, we see that these two 4K resistors are in parallel. This looks exactly like the parallel circuits we had above this section right here. So we know that there's a current split and they're sharing the current. So they're in parallel. Okay, so how do we calculate the R effective? We just go back to our formula. 1 over R1 plus 1 over R2 all raised to the negative 1. So we have 1 over 4 plus 1 over 4 raised to the negative 1. And that's going to be equal to 2. So we have 2K. And we're going to redraw the circuit again. Now, we keep doing this process until we get to the very end. And we get just one resistor and a 1 voltage source. So we have 1K here. And we have 2K here. Now, this is just a simple series circuit that we had above. We had a similar circuit. So we could simply add the 2K and the 1K in series. So we have 10 volts here. And then when you add something in series, you know that the R equivalent is R1 plus R2. So this is just 1 plus 2. And you're going to have 3K here. And this is our final circuit. That's what it breaks down to. And what you could do is you could solve for the current again using Ohm's law. V equals IR and rearrange for I and solve for the current going through right here. And we know that it's going to be 10 volts over 3, which is approximately 3.33. This time it's going to be 3.33 milliamps just because we have the resistor in kilo ohms instead of just ohms. So that's going to be it for the video today. Next video is going to be a little bit more complex circuit analysis. So I'll see you guys then.